OCR Chemistry A 6.3.1 Tests for Organic Functional Groups. There are simple identifying tests for a number of functional groups, including alkenes, haloalkanes, phenols, carbonyls, aldehydes, primary and secondary alcohols, and carboxylic acids. We'll start with simple test tube identification of the alkenes. The alkene functional group is identified by the rapid decolorization of bromine water. So here is some bromine water. Here is our unknown sample. Bromine water is orange. You are expected to know and recall that. Alkenes tend to be colorless liquids. We mix some drops of bromine water into the alkene, and the bromine water generally will form the lower layer and be rapidly decolorized, that is, go from orange to colorless. Haloalkanes are identified by the precipitates formed on hydrolysis by aqueous silver nitrate. The hydrolysis of the water component of aqueous silver nitrate causes the release of the halide ion. It's the halide ion that then reacts with the silver ion to form the precipitate. So if we have a chloroalkane, a bromoalkane, and an iodoalkane, the test is carried out by adding aqueous silver nitrate and some ethanol to aid solution, and the mixture is warmed gently. You get three different color precipitates, which I've approximated to on my drawing program. A white precipitate of silver chloride shows that the haloalkane was a chloroalkane. A cream precipitate shows that the haloalkane was a bromoalkane, and an iodoalkane forms a yellow precipitate. In each case, it's the silver halide. So silver chloride is white, silver bromide, cream, silver iodide is yellow. Carboxylic acids, like most other acids, react with metal carbonates to release carbon dioxide gas. So if we have a solution of a carboxylic acid, to identify it as a carboxylic acid, add some metal carbonate either as a powder or as a solution. The result will be bubbles, effervescence, bubbles of carbon dioxide. Carboxylic acids will effervesce with metal carbonates. Phenols are identified in two steps through their acid-base properties. Phenols are very weak acids, that is, this equilibrium with the loss of a proton lies very much to the left. So the first step to identifying a phenol is to firstly establish that it is acidic, that is, phenolic solutions turn blue litmus red and have a pH of 5 or 6, confirming weak acid status. However, they are not strong enough to react with carbonates. On the previous slide, we saw carboxylic acids produce bubbles with carbonates, with metal carbonates. Phenols are not strong enough acids to do that, so if you mix as a second step phenols with metal carbonates and there are no bubbles, the conclusion is one has a phenol. So two steps. First of all, establish that your organic molecule is acidic with a pH of 5 to 6. Then that there are no bubbles formed with the carbonate. That will confirm that you have a phenol. The carbonyl functional group is identified by its reaction with 2,4-DNP. So this reaction will be shown both by ketones and by aldehydes. Carbonyl compound, aldehyde or ketone, and 2,4-DNP, dinitrophenylhydrazine. Add drops of 2,4-DNP to the carbonyl. There's an immediate orange precipitate, or you may have to wait for the orange precipitate to form. In both cases, that is a positive identification of the carbonyl group. The aldehyde functional group is distinguished from the ketone by identification with Tollens reagent, which you may know as the silver mirror test. Tollens reagent is a solution of maniacal silver nitrate. It's formed by adding ammonia dropwise to silver nitrate solution. So starting with your aldehyde molecule and Tollens reagent, stand the mixture in a hot water bath for some period of time. A silver mirror is produced. Silver is reduced from its +1 state to its elemental state and forms as a precipitate on the glass. So we get a silver mirror. That is a positive test for the aldehyde functional group. The ketone, just to cover the ground, will show a positive 2,4-DNP but a negative Tollens reagent test. So an aldehyde, positive 2,4-DNP, positive Tollens reagent. A ketone, positive 2,4-DNP but a negative Tollens reagent. The first of those oxidations is by acidified dichromate. Typically acidified sodium dichromate, and there is the formula. The color of a dichromate is orange, and you place that into a test tube in a hot water bath. Now an aldehyde will be oxidized to a carboxylic acid. Could you complete the equation for the oxidation of propanal to propanoic acid? Pause, come back to check. Okay, so we write propanoic acid out, and then we realize we need to balance with an oxygen, which we indicate inside, comes from an oxidizing agent by placing it inside a squarish bracket. Now, the color change is caused by the reduction of chromium. Could you work out the original oxidation number of chromium in sodium dichromate and suggest the oxidation number to which it is reduced? That's a matter of recall. Pause, come back. Okay, so the chromium in the dichromate is at the oxidation number +6, and it goes to, as a factual matter, chromium 3, which is green. So if an aldehyde is oxidized, the chromium is reduced. It's a redox reaction. But only an aldehyde will do that because ketones are not oxidizable. So if your molecule, your carbonyl, which has shown a orange precipitation with 2,4-DNPH, changes orange dichromate to green dichromate, we know that it is an aldehyde. If there is no reaction, then we know that it is a ketone. However, a word of warning, on its own, dichromate, orange to green, indicates possibly that you've got primary or secondary alcohols, because they also are oxidized by dichromate. So the identification of an aldehyde requires, in this case, the 2,4-DMPH first, and then the reduction of chromium-6 to chromium-3. Primary and secondary alcohols are distinguished from tertiary alcohols by their oxidation by acidified potassium dichromate. So acidified potassium dichromate is strongly orange in colour. So you add the dichromate to the organic molecule, which may be a primary or a secondary alcohol. You warm in a water bath, and in a relatively short time, a green solution is formed of the chromium 3+ ion. Primary and secondary alcohols will show this change, as indeed will do aldehydes. So aldehydes may need to be eliminated via the silver mirror test on the previous slide. So slightly different advice to normal at this stage, as the content of this lesson is essentially recall. I would recommend that whilst keeping this slide in front of you, you write down the identifying tests for each of these 7 functional groups in turn. Then go back through the slides and make corrections. Perhaps repeat until you're 100% secure in the identifying tests for each of these functional groups.